The study of prime numbers is perhaps one of the oldest pursuits in number theory. We're going to just barely scratch the surface of it here. The first object we need to look at is the prime counting function pi of x. This function is defined as the number of prime numbers that does not exceed x. We can see a few of the values that it takes in this chart. There are a couple simple observations about this function. First, it is a type of step function. It's constant except possibly at an integer, and it only jumps up if that integer is prime. When there's a jump, it only ever jumps by 1. Second, this is a very irregular function. Because the primes are not distributed in a regular pattern, it is not immediately clear when and how often it will jump up. The challenge for mathematicians was to find a good approximation of this using a smooth function. Gauss was the first to conjecture that x over ln x was the approximation that mathematicians wanted. This was eventually proved true using some fairly advanced techniques involving complex numbers. The proofs of this claim are beyond the scope of this course, so we won't go into any of those details. Instead, we're going to prove some simpler properties of pi of x in order to get a little bit of the flavor of the types of analyses that need to be done to derive information about it. Theorem. The limit as x tends to infinity of pi of x is infinity. Notice that this theorem simply states that there are infinitely many primes. Assume that there are only finitely many primes and label them p1 up through pn, and let m be the product of the primes plus 1. Notice that if we divide m by any of the primes in our list, we get a remainder of 1. This means that none of our primes can divide m. But under the assumption that we've listed all the primes, this would say that m doesn't have a prime factorization, which would contradict the fundamental theorem of arithmetic. Therefore, there must be infinitely many primes. We can actually use this process to try to generate an ever-growing list of primes. The value pi of x over x gives an approximation of the proportion of integers less than x that are prime. In many situations, this value is more insightful than just pi of x on its own. We will now prove a quick result that bounds this value from above. This may look like an unusual formula, but formulas of this type are fairly standard in number theory. Theorem. If k is any positive integer, then pi of x over x is less than phi of k over k plus 2k over x. In this proof, we will be using the greatest integer function, which takes a real number x and returns the largest integer that does not exceed x. For example, the greatest integer of 5.9 is 5. Let x be a positive real number and let k be a positive integer. We can divide the greatest integer of x by k using the division algorithm to get that the greatest integer of x is equal to k times q plus r, where 0 is less than equal to r less than k. We will now break apart the integers from 1 through the greatest integer of x into q groups of k consecutive integers, plus one more collection corresponding to the remainder. In the first set of k numbers, we know that there cannot be any more than k primes because there are k total integers in that set. We can probably make a better estimate, but it's not necessary for this proof. From among the next set of k numbers, only phi of k of them can be prime. To see why, let's suppose that a is some value in the set that is not relatively prime to k. This means that there must be some common factor of a and k that's greater than 1. But we also know that this common factor of k must be less than k. In other words, there's some number greater than 1 from the first set that divides both a and k, so a cannot be prime. In fact, this logic must be true for all the remaining full rows of k numbers. In the last row, we will once again use the worst case estimate and note that there are more primes. Therefore, we must have this inequality. Notice that k times q is less than or equal to x, so that q minus 1 is less than x over k. Also, notice that r is less than k. These substitutions allow us to manipulate the equations a little bit more. In class, we're going to push this equation even further and show that pi of x over x goes to 0 as x goes to infinity. In order to do that, we're going to introduce an interesting trick that combines infinite geometric series with the fundamental theorem of arithmetic. This trick is tied to the Euler product formula for the Riemann zeta function, which is an extremely important object in analytic number theory. Unfortunately, it's also well beyond the scope of this class. However, if you search the internet for the Riemann zeta function, you will find plenty of information about it. I recommend the videos by number file as a starting point.
Thank you for watching this video. I'm currently dabbling with the idea of creating more videos like these for my classes, and I welcome constructive comments that might help me make better videos in the future.